Hello everyone, I'm Mustafa Sanem, and today I'll be presenting to you the reproduction of the study of the VGNN and the electronic health records. Our goal in this project was to reproduce the core claims of the original paper, which was the reproduce of the encoder-decoder VGNN modules from the graphs, evaluating them on the public dataset using the MIMIC3 and EICU. Also later on to compare the results with the original paper, and then exploring attention patterns, singular values that match the findings with the original paper. The original paper proposed learning patient presentation by treating each medical code and diagnosis procedural labs as a node in a fully connected graph. It uses graph attention to module between codes and as a variational regularization layer to stabilize the latent representation. The key claim is that the variational regularization improves robustness and predictive performance. We produce results using only the publicly available datasets, which were the MIMIC3 and EICU. The MIMIC3 used the mortality prediction, and EICU used the admission prediction. The Alzheimer's disease EHR was not used in this work, as it's not publicly available. And also it's important to note that dataset is about 30 to 40 times larger than the MIMIC3, and also the paper heavily focus on it. Also, you can see that we distributed the set as the original paper. We did 80 as training, 10 as validation, and 10 as test. Some of the samples had an imbalance, and we had to overcome it through oversampling and duplicate that when we did the training set, so we can later use even numbers in the processing part. We also do the same total of the graph and then try to code it, but instead reuse them. Here we can see the encoder-decoder VGN module detect. We can see that both of them shared the same core detect. There was only main difference in them that the VGN treats the decoder representation as a distribution and applies a regularization terms to encode smooth and more stable latent embedding. But both of them shared the same logic for the multi-hot input that is going to the embedding layer. The graph attention applied overall active nodes, a decoder attention node every shape, the final graph, and the classifier produces the final prediction. We found out the original paper did not use a KL weight, but in our experiment we discovered that the KL term overwhelmed the BCE loss. So we introduced a beta weight to balance the KL contribution, and we tuned beta to prevent training collapse. This turned out to be necessary due to our smaller batch size and fewer epochs. Here we compare our results with the original paper across both datasets. Let's start with MIMIC3. Our encoder-decoder baseline achieved an EUPRC of 0.4739, while the paper had 0.6962. This gap was expected due to the paper having trained on 50 epochs on a V100 GPU, while we trained for only 20 on a T4. Later, when we switch to VGN, we see the same direction trend as our original paper. The performance improved as we introduced KL regularization. The best performing module when we use the KL weight 1.0, which we got as 0.4976, matching the paper claim that moderate KL produces the strongest result. Now for EICU, the numbers are lower overall, which mirror the paper, since EICU is more sparse and less feature-rich. Again, encoder-decoder performs worse than VGN. Our best results appear at KL weight 1.0 with 0.2291 compared to 0.3986 from the paper. Even though our numbers are lower, it's largely due to the hardware limits, fewer epochs, and the absence of the third dataset, the ADEHR. We successfully reproduced the qualitative behavior, which was showing that the VGN consistently outperforms encoder-decoder and moderate KL regularization performance the best, and performance trends match the original paper on both datasets. We implemented everything in PyTorch with our code. We preserved the same data preprocessing steps from the older pipeline and ensured the same train validation test splits. Due to memory limits, we use very small batch size, 8 to 16, and we were limited to 20 epochs, which significantly affect convergence of attention-based modules. Here we can see the PCA plot for encoder-decoder that shows our line embedding don't form meaningful clusters. Instead, they look like a noise. This is likely due to fewer epochs, smaller batch size, and the lack of the third data set, the ADEHR. So while we reproduce the directional trends of the paper, the internal representation quality is clearly weaker in our reproduction. Here we visualize the attention width from the first layer. We found that for the positive samples, the attention widths become more concentrated. Certain medical codes receive more stronger importance. Also, what we noted that the VGNN produce cleaner and less noisy attention patterns compared to encoder-decoder, which we can see here. The encoder-decoder attention tends to become more uniform, confirming the original claim that the module oversmooth without variational localization, and encoder-decoder is more noisy than VGN. Now we move to SVD, which is singular values. SVD allows us to examine the diversity of information flow on the graph. The original paper reported that the VGN singular values are orders of magnitude larger, indicating literal element structure. The same thing is applied in our production. VGN does have slightly larger singular values than encoder-decoder, but not orders of magnitude. This is likely due to our we trained it for far fewer epochs. So the direction matches the paper, but the scale does not. The challenges we faced during our production of the paper was a severe GPU memory bottleneck due to fully connected attention, longer training times per epochs, extremely small batch sizes required on Colab, inability to train for 50 epochs as the paper, lack of ADEHR dataset, which limits generalization and stability, difficulty in matching the autometric values, even with identical code structure. To summarize, the qualitative result of the original paper are reproducible, VGN is more stable and expressive. The qualitative results are not fully reproducible under realistic compute constraint. Training for only 20 epochs significantly restrict performance. Variational localization matters, but only when carefully weighted. Also, that the KL did improve our representation quality. Overall, we conclude that the paper is directionally reproducible, but achieving the same absolute metric requires substantially stronger hardware and access to ADEHR dataset. Thank you.